So, let's look at the first example that I give you here. Okay. We are asked to find the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. So this is going to be a lot different than what we have thought of doing before. We've got to, first of all, we've got to graph these, and let's start with x equals y plus 1. Now, I could try to graph that in terms of x, but I also could really just solve that for y really easily, right? So if I subtract that 1, then I've got y equals x minus 1. So I'm going to just change that to what I know how to graph, because lines we can just rearrange real quick. So I think we need to go from like 3 to negative 3 on our axis. Alright, so if I graph y equals x minus 1, then that has a y-intercept right here at negative 1, and then a slope of up 1 over 1. Now that is y equals x minus 1, but it's also x equals y plus 1. And if you really want to think about things backwards, it has an x-intercept at 1. There's your plus 1 is your x-intercept. And its slope is still 1 here up 1 over 1. But it would be backwards. You'd really be going like over 1 up 1 over 1 up 1. Your slope would be backwards if it were solved for x. But lines, just solve them for y. Graph them like we always do. X equals 3 minus y squared. That one, I could try to solve it for y and graph it, and that's an option if you want, but let's think about what that's going to look like. If I have an x equals and there's a y squared, what does it look like? We did these in pre-cal, but it's been a pretty long time. Yep, it's a parabola, but it's sideways, right? So it is going to have, this right here is your x-intercept. And so, let's do this in red. So, x-intercept is at 3. And it's going to have the same shape as a parabola, but it's going to be on its side. And it's going to open, it's got a negative in front of the y squared, which a negative in front of the x squared would tell you it opens down, like a frowny face, right? Whenever it's sideways, what does a negative tell you, right or left? Left. So it's going to open this way. So I still do the same pattern for the quadratic. It's just turned over sideways. So I would go up 1 over 1, and then I would go up 2, left 4 from that point right there. So it's the same pattern as the quadratic. It's just been turned sideways. And then I don't know if my other one will fit over here, but it ended up over here. And then here I'll do the same thing here. And I think that's going to conveniently fit right there perfectly. So I've got this graph. Okay, so that is x equals 3 minus y squared. So let me lock this in place right now so that I can erase stuff. Alright, so whenever we're looking at this, everything we've done so far, we looked at top function minus bottom function. Alright? So, and we're looking at, let me highlight it, we're looking at this region right here. So, if I tried to do top function minus bottom function on this problem, then, like up to here, I would be fine, right? It would from -1 to, and you don't need to necessarily write this down because we're going to do it a different way. But from negative 1 to 2, then I would have y plus 1 minus 3 minus y squared. Well, there's some problems with that, but let's just go with it for right now. So, but from negative 1 to 2, what happens from 2 to 3? What's my top function? It's the 3 minus y squared. What's the bottom function? The same thing. We can't and you can't, if you subtract something from itself, you get 0. It doesn't actually find the area. And actually, this has a lot of problems right here because what I'm considering is I'm thinking of all these rectangles that go this way. So the height there, like I'd have to have this in terms of dx, but I've got y's inside of my parentheses, and you can't integrate when you have y's and a dx because that width of each of those rectangles would be dx. So we can't do this. So let's erase what we had there. Let's go back. All right, so what we're going to do on a problem like this, it actually can be done that way. You've got to solve both of these equations for y. You've got to make this like two separate equations with a positive and negative. But we're not going to go into all that because there's a much easier way to do the problem than trying to get it to work out with the x's. What we're going to do is we're going to think of this not in terms of x, but in terms of y. So rather than having, like here, whenever we did this problem, the height of each function was your f of x or g of x, and then your width was dx. So if I think of this where my little rectangles that I'm finding are like this, if they're horizontal, right, then the height of each rectangle would be dy. Right, so the height of each rectangle is dy. The width of each one is going to be like f of y. It's going to be in terms of y, right? So whenever we're doing this, we are no longer thinking top and bottom. We are thinking furthest to the right minus furthest to the left. Okay? Because if you think kind of like we take, let's see if I can get it to do it. If we take all, I locked it in place. I think I've messed it up. I can't turn it. But if we take all that and we like turn it so that it looks like it's the x and y axis, then you can sort of think what would be on top or bottom. But we're thinking in terms of what's furthest to the left and furthest to the right. That makes this problem a lot easier because what is always furthest to the right? The parabola, right? So we can integrate and we can do the parabola 3 minus y squared minus the line, and it needs to be in terms of y too. So even though we solved it for y to graph it, we want to use the y plus 1 whenever we do this. And since we are looking at like horizontal bars here, this is a dy problem. Now here's one more thing that's a little bit tricky about these. Whenever you integrate here, your limits of integration, since everything's in terms of y, they come from your y-axis, not your x-axis. So like this point right here is your lowest point. It is at negative 1, negative 2. Alright, and then this point, let me use a different color for that. Alright, so negative 1, negative 2. And then this point right here is your highest point, and it is at 2, 1. So when we're doing limits of integration here, we're thinking everything is horizontal. So the lowest point, we use the y-coordinates, not the x-coordinates. So the y-coordinate there is negative 2. So we will integrate from negative 2 up to the highest y-coordinate there is our positive 1. So we integrate from negative 2 to 1. It looks like, if you're thinking in terms of x, you should integrate from negative 1 to 3, because that would be from left to right, and that's what we've done so far. But whenever we're in terms of y, we have to do the lowest y to the highest y. goes to the right, yes. Yeah, so it's right is the same as top whenever you're doing these problems, and left is the same as the bottom. Kind of like if you're looking at graphing something or shifting something left or right, the right is your positive direction, left is your negative direction. So up is your positive direction, down is your negative direction for those. So if you can get it to this point, which I think is a little more confusing because, not so much because it's more difficult, as I've done a lot of these problems, it's not that difficult, but we're not familiar with graphing things that are solved for x, and we're not as familiar with looking at this sideways. As you do more, it'll become easier. But once you get it to this point, integration is the same as it is with an x. As long as your y's and your dy match here, you integrate just like you would. So for solving it out, it's no different at all. So you'll have 3, well, let's see, let's go ahead and put everything together. So you're going to have that 3, and you're going to have to subtract that 1, so you'll get 2 minus y squared minus y dy. And then you will have, that'll give you 2y minus 1/3 y to the third minus 1/2 y squared. And we will evaluate that from -2 to 1. So I'm going to, because I don't want to spend an incredible amount of time going over this one, I'm really mostly concerned with you knowing how to set it up. I'm just going to go ahead and use the calculator for this. 2 times 1 minus 1/3 times 1 2/3 minus 1/2 times 1 2/3. So that first is going to be 7/6, and then when we plug in 2, we'll have 2 times -2 minus 1/3 times -2 2/3 minus 1/2 times -2 2/2. Hope I put everything in there right. So that gives us -10/3. So we're going to have 7/6 plus 10/3, and we're going to 9/2. And it is fine with me on your homework if you do what I just did there, because our book is not always friendly on giving us ones that you can do really quickly by hand. So integrate everything by hand. Don't use the integrating feature, but you can type this in on your calculator at the end. Usually AP limits the amount of stuff you have to do for that, and if it's free response, you can leave it. You could just plug in the numbers. You could leave it 2 times 1 minus 1/3 times 1 to the third minus 1/2 times 1 squared minus, and then just leave the whole thing like that if you wanted for free response. And here's our next one. Alright, so we've got x equals y to the third, x equals 4y, y equals 0, and y equals 2. So let's sketch a graph of this first. And this one is one that you could do either way pretty easily. And we really need to go on out to like 8 on our x-axis. So x equals y to the third. It's like a quadratic, it's like a cubic, but it's sideways. Sometimes I have a hard time really thinking about this. So if you think of making yourself like an XY chart, think of plugging in y values instead of plugging in x values. So like if we plug in 1, then 1 to the third is 1, so we get a 1 for the x. If we plug in 2, 2 to the third is 8. So we get an 8 for the x. So it's just kind of like, normally we plug in x values. Well, if you did that here, you'd have to take the cube root of both sides to solve it. So instead, I'm just plugging in y values. So if I plug in 0, the cube root of 0 is 0. I'm not going to plug in like 3, because 3 to the third would be 27. That'd be too big for my graph. And hopefully, it's going to intersect somewhere here. If I plug in -1 for my y, -1 to the third, what do I get whenever I do that? -1. If I plug in -2, -8. So then I can graph these points. I'm going to use blue for this one. So 1, 1, 8, 2, 0, 0, -1, -2, -8. And those of you that are really good at sort of picturing that could probably just take your normal cubic function and turn it sideways like that, and it'd be perfectly wonderful. Sometimes I have a hard time doing that, though. Then for graphing x equals 4y, I still just solve this for y. So if you divide by 4, you've got y equals 1/4 x. So, and actually let me switch to red for this one. So it's going to have a y-intercept at 0, 0, and a slope of 4. So up 1 to the right 4, up 1 to the right 4, which conveniently is going to intersect at grid lines perfectly. And then same thing over here. So we get this line here. So we've got 2 areas that we're looking at. Now, the first thing I will say is you should notice when you graph this that the area between the curves on the right-hand side of the y-axis and on the left-hand side, those should be equal to each other. You can see the symmetry of the graph, that those are going to be equal. So if we only found one side, then that would still be okay. We could just double it and get the area. So that's what I'm going to do here. When you notice a graph has symmetry, I would encourage you to do that. So let's just deal with this green area that I have marked here. I'm going to show you both ways you can do this problem. This one, do you have a clear top and bottom? You do. Do you have a clear left and right? Which one is always furthest to the right? If we're only looking at this section that I have here. The line is always furthest to the right. The blue curve is always furthest to the left. All right. So we could use either method for this. So I'm going to first do it with the y's because that's kind of what we're looking at, and I'll show you how to do it with the x's as well. So the reason the y's are a little bit easier here is because both of your equations are already solved for x. So it's already in terms of y. So if I'm trying to do this in terms of y, then I would do the integral, and I would say 4y, because it is always furthest to the right, minus y to the third, and I would put a dy over here on the end. What would be my limits of integration? It is not 0 to 8. It is 0 to 2, because it's got to come from your y-axis. So like this point, right, like this point is 0, 0, and this point is 2, 8. Oh, it would help if I gave you the right coordinates, 8, 2. So if we're doing the problem in terms of y, then we have to use those y coordinates as our limits of integration. And so if we do this problem, we're going to have 2, and actually let's put a 2 out front because we've got to double it. So we'll have 2y squared minus 1/4 y to the 4th, and we'll evaluate that from 0 to 2, and that's going to be 2 times 2 squared minus 1/4 times 2 to the 4th, and we'll have minus 0 there. So that's going to be 8 minus 16 divided by 4 minus 4. So we'll just get 8 for our answer there. Okay, questions on that? All right, now let's go back and do the same problem in terms of x, because you can do it that way as well. If you are doing this in terms of x, let me use green for this. So in terms of x. Yes. So start at somewhere where they're intersecting, right? Start at the y-axis. So as you travel to the right, which one is furthest to the right? It would be the red function, no matter where you're at, right? So no matter where you're at, if you start at the y-axis, that red line is further from the y-axis. It's furthest to the right every time. And then if you start at the y-axis, the blue line, it is left. It's closest to the right. So think of starting from that y-axis and look at which one is furthest to the right, which one you have to go furthest this way to get to, or the one that you have to go the least amount. Now, if we go back and look at the last problem, the reason I'm hesitant to just say furthest from the y-axis and closest is because, like right here, when you get down to this this red is closer to the y-axis, but it's still further to the right than the blue line, right? So it's still furthest, you want to say furthest to the right, because you can. Yes. Like if you could take all this, I might actually be able to. Oh yeah, I can. Let me group this together. Like if I take this and I turn it sideways, you can think which one's top and bottom. So the red would be on top, the blue would be on bottom. You're taking your positive x-axis and making it your positive y-axis there. But I would suggest try to think from, like if you start here, if you start at your y-axis, which one, go to the right, look at, or if you're over here on the right side somewhere, which line's closest to you, right? So if you're over here, which line, if you go horizontally, which line's closer? And so everywhere, at least in this interval, right, everywhere that red line is closer to you if you're standing over here on the right side. Whereas if you're over here, everywhere the blue line is closer to you. As long as we're only looking at that green area. Now if we were looking at the bottom part here, it would switch. The blue is furthest to the right down here at the bottom. But we're kind of ignoring that and just doubling it since it's symmetric. Now you can do this problem in terms of x. But if you do, you must take both equations and solve them for y first. So like x equals y to the third, you've got to take the cube root of both sides. So that blue line right there, it is also y equals the cube root of x. And you would have, we already solved this one right here for y. We already solved the line for y. It would be y equals 1/4 x. So if you're doing it in terms of x, with vertical like top minus bottom, then your equations have to be in terms of x. So if we're thinking top minus bottom, which function is on top? The cube root, right? That blue line, right? So that cube root, we would integrate the cube root of x minus the line, which is 1/4 x. And we would put a dx here. Now, on this one, what would our limits of integration be? 0 to 8. So here you can see, like, we are using 0 to 8. We're using those x coordinates for our limits of integration. And we would also, on this one, put a 2 out here, out front, because we're going to double whatever we get. And I am going to not go ahead and integrate all that. You can see the appeal of y here, because you don't have to solve these. Plus, 4y minus y to the third is a lot easier to integrate than x, the cube root of x minus 1/4 x. So it is better to do y, but if y is sort of like blowing your mind on a problem like that, you could do it with x's in that case. The first one we did would be pretty hard to do with x's. Okay, here is our next one. Okay, this next one can be done either way as well, and we're going to look at both ways. So we've got f of x equals 3 over x, x equals 0, y equals 1, y equals 3. So let's graph this. X equals 0 is the y-axis, y equals 1 is a horizontal line at 1, y equals 3 is a horizontal line at 3. So we really I don't think we're going to need we really just need the first quadrant here. Right. Alright, so I'm going to graph all these lines first. So x equals 0, x equals is the vertical line. I know it seems backwards, but it is. So it's just the y-axis. Y equals 1 is going to be a horizontal line at 1, and y equals 3 is a horizontal line at 3. And then the one that is a little bit harder to graph. So we've got 3 f of x equals 3 over x. So I would just graph this by plugging in some numbers. If I plug in 1, I just make myself a chart, x, y. If I plug in 0, it'd be undefined. If I plug in 1, what do I get? 3. So 0.13. Let me use purple for this one. 13. Okay. If I plug in 2, what do I get? 3 halves. So 1.5. So let's graph that point about right here. And if I plug in 3, what do I get? 3, 1. So 3, 1. Conveniently, that hits these lines. So this is a curve like this. You're going to have a vertical asymptote on that and a horizontal asymptote, but it's not in the region where it really matters there. So with these lines, we are looking at this area here. Okay, so I'm going to show you how to do both ways for this one as well. So, which one do you guys want to do first, X or Y? Y, okay. So, with respect to Y. And Y has an advantage here because if I'm standing over here on the right, which line is always closest to me? The purple, right? And which is always furthest away from me? The red, right? So we're doing purple minus red. So for this one, now we do have to be careful because is my purple line solved for Y? It is not, but we can solve it for Y pretty easily. So Y equals 3 over X. What would I have to do to solve that for Y? Multiply by X, so that gives me XY equals 3, and then divide by Y, so X equals 3 over Y. It's one of those functions that is its own inverse, which is kind of weird. So, so this is 3 over X, but it's also 3 over Y, right? And this right here, I really don't need a special function for because it's just 0, right? It's already in terms of X or Y, whatever you want it to be in, because it's just a number. So, I guess it's Y because it can be Y because it's the Y-axis there. But so we are going to integrate 3 over Y minus, the purple line is 3 over Y. What's the red line? 0. So we really don't even have to write that. dy. What should my limits of integration be here? 1 to 3, because I'm looking at the y-axis for those limits of integration. So here I've got 1 to 3, 3 over y, dy. What do I get when I integrate 3 over y? 3 natural log of absolute value of y. And I'll evaluate that from 1 to 3. So I'll have 3 natural log of 3 minus 3 natural log of 1. What is natural log of 1? It's 0. So we end up with just 3 natural log of 3. Okay. So that can be done. It's a little easier to do it with respect to y if it makes sense to you when you see it. But let's go back and look about what we would do if it's with respect to x. Alright, so if it's with respect to x, we're no longer thinking right versus right minus left. We're thinking top minus bottom. So is the same function always on top? It is not, because right here it switches. Okay, so that means we're going to have to do 2 separate integrals for this. Or, well, we could do 2 separate integrals, but what is this area right here? Nice, beautiful shape that we know how to find the area of, right? So if it was a different function, it might be worse, but we know how to find that area. So we could just say length times width, which is 2 times 1. So we could just say that part is going to be 2. Right. Then we would have to add our integral here. So here, what is the top function? The f of x. So that is 3 over x. And what's the bottom function? 1. And what would be my limits of integration there? It's not going to be 0 to 3 because I already did this part with the rectangle, so I'll do 1 to 3, which has nothing to do with the y limits, which happen to also be the same, so try not to get that confused. We're looking on the x-axis here, 1 to 3. So you can see this was a little bit easier to integrate, but this one's not too bad. You've got 2 plus, when we integrate this, we're going to get 3 natural log of x, absolute value of x, I guess, minus x, and we're going to evaluate that from 1 to 3. We'll have 2 plus, and then we'll have 3 natural log of 3 minus 3 natural log of 1 minus, hold on, messing that up, 3 natural log of 3 minus 3 minus 3 natural log of 1 minus 1, that is parentheses there. So, got 3 natural log of 3 minus 3. What is the natural log of 1? 0, so that goes away. We'll have a plus 1 here. And so the 2 minus 3 plus 1 all cancels each other out, so you just get 3 natural log of 3. So I think that one's easier to do if you do it in terms of y, but can be done either way. The first 2 problems kind of give themselves away that it would be easier to do them with y's because they're solved for x. So that should be like an alarm to you. If you see it's x equals y, that should be an alarm. There's one more thing we're going to look at, so hold on just a second. And then this is y to the third and y for y. So that should make you think y's are going to probably be easier. A problem like number 3 doesn't really have that, but if you think of setting it up both ways, you might be able to see which one is easier. All right, this last thing, I just want us to graph this right here, although we could do the whole problem, but I want us to graph this right here because I'm afraid we don't really know how to graph it so well because it's a little bit difficult. Okay, so we have to be careful whenever we graph a quadratic sideways because usually that plus 4 right there would tell me to go up 4. And usually that minus 1 would tell me to go to the right 1. But everything's backwards whenever you've got x equals. So this y right here, that's going to tell me up or down. And since it's in the parentheses, it goes the wrong direction. It goes the opposite direction. So this tells me to go up 1. And so if that tells me to go up 1, what's that plus 4 going to tell me? It's going to be right. Because it's on the outside of the parentheses, normally left and right is backwards and up or down is the correct direction. It's going to be, everything is opposite when you do one of these. So, and this negative tells us that it's going to open to the left instead of to the right. So if we graph this, it's got to go to the right 4, it's got to go up 1. So right 4, up 1. Your vertex is going to be right here at 4, 1. And then it's going to have that parabola shape open to the left. So your graph would look like this. Let's just graph in this other one just so we can see real quick. We'll have negative 1, up 1 over 2, up 1 over 2. So we would get this little sliver right here. I'm not going to do the whole problem, but let's just think about how to set it up. We would do the integral. Which one is furthest to the left? The blue or the red? I'm sorry, furthest to the right. The blue or the red? It is the blue. For the section that we're interested in right here. Right. So in this area, if you're over here on the right side, the blue is closer to you. So you would have negative y minus 1 squared plus 4. And then the red, it'd have to be solved for y first. You'd have to add 1, y plus 1 equals 1/2 x multiplied by 2. So you'd get 2 times y plus 1 there, dy. And what would the limits be? From what to what? Perfect. Negative 1 to 1, because your y coordinate is negative 1 here. Your y coordinate is positive 1 here. Okay, the assignment for tonight is on page 414. And sorry, let me check this to make sure. 17 and 18, and then 27 through 30. Oh, let's see. Let's not do 30. Let's do 27 through 29 and then do 31. Because I don't know how to graph 30. I think you could do it without the graph, but let's just do it. Yes, all of these are without the calculator until you get down to that very last part.